Hi everyone, David Haller, and I'm going to tell you a bit about the latest stuff we've developed in FESafe and the 3D Experience Durability Portfolio over the last year and a half, 2 years maybe sometimes. Some things we still like to remind people of. Why? Okay, there's the usual legal notice here. I'm going to skip through that. So we're going to cover these topics here. I'm first going to give you a little bit of an overview of the 3D Experience durability capabilities, then talk a bit more about weld fatigue. There's overlap there actually between FSafe and 3D Experience. An update on the TCD, theory of critical distances. A little bit about our new thermomechanical fatigue capability. And I'll have a couple of slides that have a bunch of bullet lists on some general enhancements. Okay, just our 3D Experience durability interface. It's totally integrated into the mechanical and structural scenario apps. So you define your analysis steps and initial conditions, boundary conditions, loads, constraints, interactions, and the durability features all within the same app. As you can see, we have this action bar along the top here. Here's our durability section. Some of these things have changed since the last time you saw it because there's been some changes in general in mechanical and structural scenario. And we have automated execution and chaining of the execution of the structural analysis, which runs Abaqus, of course, and durability analyses, which, of course, runs the FESafe solver. Okay. And you can, you get this kind of interface when you click on the simulate button, gives you some options here, right, about where you want to run it, how you want to run it, and all this kind of stuff, right? A little overview of the different roles that we sell. There's quite a bit of confusion out there because we have a lot of roles. So in the 2021X releases, we have these, what we call SIMULIA Works portfolio roles. Durability performance engineers and durability and mechanics engineers. These are our lower end roles. They enable you to do base metal fatigue, but they exclude weld fatigue. Okay. You get embedded compute automatically up to 8 cores, and you can use sim units or tokens like things for, if you want to run on more cores. Just as a note, whereas Abaqus can use MPI, multiple compute nodes, FESafe really only runs on one compute node, but these days people have lots of cores on that one node, so it's not normally needed to do any go beyond that. Then we have another role here, structural and durability engineer. These are the trigrams for them. These basically cover the exact same things as these works portfolio roles, but you get embedded compute for up to 32 cores. Yeah. And of course, you can, if you have compute nodes with more than 32 cores, you can also use sim units and tokens, those kind of things, right? So our highest end role is structural analysis engineer. There's another one also called something like composites engineer, which also contains all the durability capabilities, weld fatigue included, right? And weld fatigue includes both FKM and Verity-based weld fatigue now. A little bit of an overview. This is the fatigue loading dialog box. Those of you familiar with FESafe will recognize it's got the same style of tree structure, but the way we refer to stress data sets is much more general and flexible, allowing you to integrate much better with our process apps if you want to automate workflows. I have to move fast. Yeah. Something new in. So most of what was here was it was there before in 20x, 21x, and 22x. Includes some plotting of the signals when you attach a signal to a frame of data of stresses, for example, and you want to see that, you can plot the signal now. In when you and that includes in your if you're in an FKM analysis case, instead of applying a signal, it's quite common for users to apply what's called what the FKM thing calls guidelines calls a stress spectrum, and that's just basically it's like a histogram of stress amplitude factors and scale factors and mean stress scale factors, and you can plot that for the number of cycles given here. Okay, it's a very simple text file that you provide, and then we'll plot it to make, and you get a bit of visual feedback. Material options, we cover pretty much all of the FE safe metal fatigue algorithms and all of the mean stress corrections. About a year ago, there was some restructuring into the Abaqus multiphysics capabilities and the FE safe durability capabilities under the structures organization. And here you can, for example, put in your SN curve, right, under stress life, right? So this is being shown here in MPa, but actually our default is pascals or newtons per square meter, so they probably should be a E8 on those. Our loading covers pretty much all of what FE Safe can do at this point. Superposition, sequence of frames. For FKM, there's a spectrum. Overlay events are like in FE Safe high frequency events where you can overlay one event on top of another, or multiple events can be overlaid on a sort of a base event. You can include preloading effects or manufacturing through residual stresses. Temperatures, you can specify via the temperature frames that match the stress frames or provide a uniform value. And we support driving durability now from explicit dynamics. So FKM weld assessments. This was added last year. The fatigue loading looks largely the same, except you have this option over here to add a stress spectrum to an event. And you can apply multiple assessments, and we cover, in this case, both the fatigue assessments as well as the static strength assessments. These are all from chapters 3 and 4 of the 6th edition of the FKM guideline. All right. Sometimes having trouble advancing this. Okay, there it goes. So I'm not going to go through the details here for sure, right? The main point of this is to show you that we actually provide all of the FKM parameters as available to you. In the early edition of FKM implemented in FE Safe, we only sort of showed the sort of table lookup values. We didn't actually realize at the time that people often tuned some of these factors for their own processes beyond what the tables in the guidelines say, right? So we didn't make that same mistake again. We learned from that. And this time around, we provided all of the parameters. And there's a lot of parameters, as anybody who's familiar with FKM will know. Of course, almost all of them have default values. And, we show those, and we show you, for example, here, how we get the default value and from which FKM table. Because one thing to remember is that we're never going to reproduce the FKM guideline in our user documentation, okay? You are expected to have your own copy or access to your enterprise copy of the FKM guideline and to understand the way to set these parameters. But we give the parameters that you'll see in the guideline and the tables and so forth, so that you can very quickly cross-reference between the GUI and your copy of the guideline. Currently, the FKM weld assessments in 3D Experience platform are only deal with solid models. We still have to get to working with shell models, for example. We only actually also do weld assessments today. We don't do base metal assessments yet either. Okay. You can have any number of weld assessments. If you have different kinds of within each fatigue weld assessment, for example, you can define your fatigue loading specific to that assessment. And that, of course, can have multiple events inside that fatigue loading. But you can have a whole different definition of fatigue loading in a different specification of a fatigue assessment. Same thing for static assessments, right? So you can effectively do a whole lot of different assessments all in one shot if you just set it up all together, right? The way the structural stresses are computed, we use surface stress extrapolation using the IIW recommendations. These are the same basic recommendations that are in British Standard and Eurocode and several other standards. Or sometimes there's not the welds are kind of too close together and you don't have enough distance to do surface stress extrapolation. So we offer an option to use through thickness stress linearization, also per many standards and codes of practice, right? One key thing here, and this is going to apply to Verity as well, you need to create compatible meshes across the interface between the weld metal and the plates. Okay, compatible meshes with nodal condensation and all that kind of stuff. Now, 3DX provides you with a lot of some very handy ways of creating those meshes in a compatible way. Now, moving on, switching from staying with welds, but switching from FKM style analysis to our Verity style analysis. So, so these were for shells and solid models. These were released late last year. The way you define the shell weld specifications for Verity is separated. It's in the scenario modules, right? But it's integrated with the line fasteners that you can create to generate meshes in a much more automated way. The line fasteners being in the model component of your simulation objects. Okay, so here you just see some realistic shells. The modeling apps all do the mid-surfacing. You can do the mid-surfacing relatively easily, and then you can mesh it, and then you can generate these dark gray fillet meshes here. And you can see you can create the fillet itself, and you can create these little vertical parts here if you have full penetration welds. And the line fasteners make that actually very easy. And there's actually quite a nice posting on this in our blog, SIMULIA blog, on how you can speed up the model build process for chassis and suspension by 10x over competitors' preprocessors. All right, so just I want to emphasize this. When you're using Verity, unlike with the F-game where you're using surface stress extrapolation, with Verity, you've got to create partitions through your geometry where the crack surfaces are going to be. All right, so if you're doing toe failure, you're going to need a partition. Here's the toe. You're going to need a partition through the plate at that point. Okay, this is not a problem for shells, of course, because as long as you have compatible meshes here, then you obviously have, you don't have a problem. But I'm talking about solids right here. Okay, if you want throat failure, then you need a partition through the throat of the fillet. If you want failure from the root down here through the plate, you're going to need a partition over there. Okay, and the same thing for the toe up there, right? Typically, you would leave this, if it's not a full penetration weld, you'd leave these two parts, this plate and this plate at this point here, not joined at all, right? And here you see the interface. You most of the time you're gonna just choose some things from the general tab here. You can, when you define it via a weld fillet set, you can solve for all the failure modes at once. Okay. And you can choose which Verity material you're going to use. Actually, I didn't. So there's another option we have here that I'm not showing is the weld line set. Okay, so if you can't get your meshes sorted out with the weld fillet set and you need a little extra control, just the way in FE Safe you have the manual method of doing weld line definitions, we have something that's much easier than the manual weld line definitions called this weld line set. And it allows you to do things with giving you a bit more control, yet still has quite a lot of automation, allows you to still do a lot of automation of building up things. So our first release of Verity spot welds came out, well, I think it's actually FD01's coming out in about 2 weeks, I think. And then we're only do the sort of ACM2 style solid hex construct today. And a couple of months later, we will support so this is integrated. The key is it's integrated with a point fasteners in the modeling, structural modeling app. All right, this allows you to create thousands of spot welds very quickly. And it also, the big advantage is it allows you to choose your modeling construct and switch between it pretty easily, and then it'll regenerate the mesh and the constraints, the distributing couplings or the kinematic couplings. It's got a lot of controls there, a lot of flexibility for you to choose the style that matches what your company has typically been doing. Okay, so in several more months, we will support what in the point fastener capabilities they call the rigid, spring, and beam constructs. The rigid and beam means it's using connector elements with couplings between the ends of the connector elements to the sheets, the shell mesh sheets, right? Today, FE Safe only supports sheet metal failure, but we're going to add nugget failure as well. And you can find that over there. The spot weld, of course, has got a very simple interface in it. Okay. And you can choose which fastener to pick from the spec tree, right? Just a little comparison between Verity and FKM welds. So you can do Verity welds along with regular base metal fatigue in a regular durability analysis case. FKM, you need an FKM durability case. Verity, we currently support solid and shell models, currently only support solid models for FKM. With Verity, you can model the fillet itself, or you can play more tricks if you want using the weld line sets. With FKM today, we only support you have to define the weld fillet sets. Structural stresses, we use nodal forces for Verity. We have two flavors, the basic and enhanced. For FKM, we use surface stress extrapolation or thickness. We do weld fatigue only for Verity. We do static and fatigue strength. Verity, you actually are getting life repeats output for the specified fatigue loading. For FKM, for the specified stress spectrum, you get a utilization. Okay, that's, you want it to be below 1. So I'm actually going to skip these. The main thing is you need the enhanced nodal force. You can use relatively unstructured meshes. That's a big advantage, especially when you want to model with TET meshes. We introduced a new theory of critical distances, or TCD interface. Okay, it's much more general now, much more flexible. You can use almost any of our algorithms. And when we do the calculations at the TCD subsurface locations, we use the exact same algorithm that you used at the surface. This makes it way, way easier to compare your surface predictions with your subsurface TCD predictions. We've created a thermomechanical fatigue plugin. It's based on DTMF technology developed at Fraunhofer IWM over the last 20 years. It's currently only available as a plugin. Later this year, we hope to build it in, but I can't make promises for any specific dates of that. This will eventually replace what we have for TurboLife. TurboLife is already in controlled availability. It will become deprecated within the next few years. We haven't sent that notice to TurboLife customers yet. If you want, it's still in a somewhat evaluation phase. If you want to evaluate it, you got to contact either me, Giovanni Demaresh, or our product manager, Pavel Sobchak. Okay. This, I'm not going through these equations. What it is, it's got far fewer. The red parameters are the ones you need to provide. There are far fewer of these parameters that you get with TurboLife. It's a fracture mechanics inspired approach, using a lot more analytical methods to sort of pre-integrate some things. We include the mechanical fatigue aspects here. This FCR is a creep term, which you can see multiplies the mechanical. And we also include oxidation. The DTMF here is the same as the one over here. So the oxidation is also effectively a multiplier effect on the mechanical fatigue. So there's several things here. The main thing is we've got unified licensing now between 3D Experience and FE-Safe, and it's unified also between Abaqus and FE-Safe or durability solves. We use the same core count numbers of tokens and credit licenses. Okay, not going through all of these other things here. Another important one to note is we now properly support durability execution on the cloud. Previously, you really had to solve, when you had a cloud role, you had to solve the durability locally, which was actually a bit of a pain. Now we cover that. Okay, I've got to stop here to give you guys a chance for some questions.
Yep, we already received a question about durability fatigue loading. Can we add residual stresses from bolts preload analysis as it was available in FE-Safe standalone?
Yes, absolutely.
Okay.
Glad to get easy questions.
And this was the only one for now. So, Pratik, I think we can move forward with Tosca for now. Maybe we're getting some additional questions later on.
Okay, then I'll try to share my screen.
Okay, I'm going to stop sharing.
Yeah, okay. So, hi everyone. As Vanessa has already introduced me, I'm Pratik and I work with the Tosca team. I'm responsible for developing topology and sizing optimization mainly. I will be taking you through the new features in Tosca Structure 2022X. Before that, there are some legal notices. I'll just let you read them and let's start. So for the ones who are new here, who haven't really heard a lot about Tosca, I would like to start by giving a short introduction about Tosca, about how it fits into industry processes and how it can help with the product development. So in a conventional setup, there is a lot of testing and validation and prototyping. And this takes up a lot of development time. It takes up a lot of, it requires a lot of money. And thus the cost and the development time is a lot higher. So what happens when we bring simulation into the loop? We offload the testing part. So we do a virtual testing now, and thus the time shortens. What we are trying to do with Tosca, we are taking this one level further. We want to have a software where the user gives an initial design. They give the set of parameters that the ideal designs should satisfy. And then Tosca iterates over the initial design and uses some mathematical algorithms to make sure that a design is achieved where all this is possible. So ideally, you should have only one prototype and one validation at the end of this process. And this reduces the development time, and it also decreases the cost of development. So we have four main offerings in the area of structural optimization. The first one is topology optimization. The idea here is to provide an optimal material distribution. So we use the element densities as design variables. And the idea here is to use this in the initial parts of the development where larger changes to a component are possible. Then there is the Tosca structure sizing. And here we want to provide an optimum thickness distribution. This is usually used for body in white structures or other sheet metal parts, and also somewhere in the beginning stage of the design. And then we have Tosca structure shape. And the idea here is to change only the outer boundaries of the part. So if it's a 3D part, then the surface of the part. And these are very small changes, so it can be done in the later stages. And the idea is to improve the stress characteristics, for example, by reducing the stress hotspots or trying to improve the durability. And finally, we have the Tosca structure bead optimization. And here we try to find an optimal bead pattern on sheet metal parts to increase their stiffness or to improve their eigenfrequency characteristics. So I would also like to talk about what sets us apart from other optimization packages. We have a very close interface with Abaqus, which means we can get the true nonlinear sensitivities for nonlinear load cases. Why does this matter so much? Let's look at this example here. So we have a simple beam here supported at the ends and then loaded in the middle. And we are trying to minimize the maximum displacement under a volume constraint. So let's say we do it in the traditional way. We need to take the nonlinear load case here and linearize it in order to calculate the sensitivities. So we make an assumption it is linear. And then with those sensitivities, we come out with a design like this. As you can see, the cross members here are in compression. And this means they're likely to buckle. And this is exactly what happens. So if we validate with the nonlinear load case on a force displacement curve, you can see there is a buckling event. Versus this, if we use the true nonlinear sensitivities, which we can get from Abaqus, then we get a completely different design. And these cross members, which were in compression, are now suddenly in tension, which means they will not buckle. And we can also validate this here. So that is the importance of having nonlinear sensitivities, and that is what sets us apart. So how did we get here? This is a short overview of our evolution. In 2017, we started by supporting topology optimization with Abaqus sensitivities. Then over the next 3 years, we consecutively added support for sizing, shape, and bead optimization. Last year, we included support for plastic strains in topology optimization and an efficient algorithm to evaluate group operators. This year, our focus is on expanding the range of design responses that can be optimized. And thus, we are introducing user-programmed design responses, principal stresses, and plasticity approximation factors. I will touch on these later in more detail. So an overview on the new features. We are focused on two major areas. The first one is improving the ease of optimization. That is to say that we are trying to make it easier for the user to understand the results that come out of the optimization, to reconstruct them, and finally get a product that is usable with the least possible effort. To achieve this, we have implemented new manufacturing constraints for both topology and bead optimization. We have also planned something for sizing optimization later in this release. Secondly, we are trying to provide more support to the advanced users in terms of the design responses that they can optimize. And we are also trying to give the ability to resume a converged optimization. So to do this, we have implemented support for multiple user design responses with different base types. And then we have some new stress responses and plasticity approximation responses as well. We are also planning to support inertia relief method in this version of Tosca structure. Before I get to those features, I just want to touch on one of the really nice features in topology optimization. It was developed in 2021, and we have been improving it since then. It's called the Unified Material Interpolation Scheme. And the idea is as follows. So Tosca chooses an interpolation scheme according to the responses present in the optimization. So if there are some mass-dependent responses, Tosca will try to get another scheme as compared to when there are only non-mass-dependent responses. So I can illustrate this problem with the example here. Let's say we are optimizing this component, and it's a volume minimization, and it has some displacement constraints on it. And if we don't have any frequency constraint, then the result looks like this. It's quite nice, well differentiated. But if we add an inactive frequency constraint, and this is something our users often do just in order to track the frequency of the component, let's say, and then suddenly Tosca takes a different scheme and the results don't look as nice as they were above. And this is an inconsistency because the user is now unable to understand what happened. So to avoid this kind of a problem, we have introduced a new scheme. It works equally well with both mass-dependent and non-mass-dependent responses. You can even combine them, and you still get the same results. And there are other benefits, like we have a better adherence to minimum member constraints. And now we have a new filtering scheme to go with this interpolation scheme, which is based on design variable filtering. So here is a short overview on how the scheme really makes a difference. This is a Norwegian SOC example. It's quite famous. It's a it's a minimized volume example with stress and displacement constraints. And to make this more complicated, we have added a mass-dependent load. It's a gravity loading here. So what happens with the older versions of Tosca, Tosca combines two different schemes, and it is really not able to find a clear result. But down here with the new scheme, it is able to get a very well-differentiated result. This can be directly reconstructed and used. Similarly, here is an industrial example. This is a component from the wheel carrier assembly, and it has a minimized volume with stress, frequency, and displacement constraints. We can't really get a good convergence with the older versions, but with the new one, we have a well-differentiated structure here. So in both cases, the scheme works better when you have combined frequency and stress, for example, and I would encourage you to use it. It is available as an option and it is already documented. So now we can come to the manufacturing constraints, which are the new features. Okay, so the first one is a new maximum member algorithm. And the idea here is that this new algorithm works by enforcing the constraint locally in the model and not as a global constraint like before. So this gives the optimizer more freedom to place the material as compared to the previous version. And what this means is we don't get floating material like this or disconnected structures like this one here. And in this particular case, we even managed to improve the objective while getting a well-connected structure and a well-differentiated structure as well. So this works for 2D and 3D equally well. The next one is a completely new feature. So this allows the user to create rib structures while optimizing the model. The way this was done previously was to use some kind of a casting constraint, maybe multiple casting constraints. But the problem is we can't really control the thickness of the ribs or the distance between two ribs or anything really. So now with this feature, we can control the thickness of the rib, the distance between the ribs, the direction as well in which the ribs are created. And this means the structure is more manufacturable. The cost here is that we may not be able to achieve the same objective function as before because we have placed more restrictions on the optimization. But ultimately, this is easier to manufacture. Then there is a feature which has been requested for quite some time. It's the plane symmetry in beat sensitivity optimization. So it is available now, and symmetry can be specified across multiple planes. The only restriction here is that the original model has to be symmetric or roughly symmetric, at least around those planes, because beat optimization makes relatively small changes to the design, and it really cannot take an asymmetric model and convert it to a symmetric one. Okay. Then I'm coming to the new design responses. This is the part which is where we hope to support the advanced users. So the first one is a really versatile functionality. It's the user subroutine design response. And the idea here is that the user can define their own responses in an Abaqus subroutine, and they can define multiple responses, and they can provide the values and the sensitivities over this subroutine. And these responses can be based either on stress or on plastic strain. And this means now it is potentially possible to do laminate failure criteria or some kind of custom stress responses, for example. And the only thing the user has to do is they have to define their response in the Abaqus subroutine, and then they have to provide the identifier to Tosca in the parameter file. And there can be multiple of these. Previously, we had the restriction that there could be only one user design response at a time, and only stress type was supported. Now we support stress and plastic strain both. Next up, is the equivalent plasticity responses. So the idea here is that it's really costly to calculate plasticity with a full nonlinear calculation, especially for larger models. So what we do here is use a linear load case, and then we try to interpolate to the true value of plasticity using Neuber hypothesis or the Glinka hypothesis. And it makes the calculation of plasticity really fast. So we have these 6 factors, the Neuber factors and the Glinka factors here. They are really useful when approximating either local plasticity effects or in microplasticity situations or for fatigue plasticity. Then we have the directional stress responses. So we have the basic principal stress, the maximum principal stress, and the minimum principal stress. And then we also have the sign von Mises stress. So this has the value of the von Mises stress, but the sign of the hydrostatic stress. And the idea here is that it functions better for materials that perform better in compression, for example, like cast iron. So this, in effect, it widens the range of materials our users can optimize for. Then we have an exciting feature. It's the Tosca resume capability. The idea is, let's say you have an optimization which runs to a certain number of iterations, and then Tosca says it has converged, but your result looks something like this here, which is not really what the user expects. So then now we can go in and we can change the convergence criteria, and we can run the optimization again from this point on, instead of having to run it from the beginning like before. And then we can adapt the settings, and then we can resume the job and get a proper design out of it. So this saves time and effort, and in general, it makes the software user-friendly for us. Okay, then coming to some features planned in the future. So we have the rib reinforcement constraint for sizing. So with the thickness controls and sizing previously, it was possible to see such effects as here on the right side. That the edges of the structure would be very thick, and the structure in the middle wouldn't be really it wouldn't have a good thickness distribution, and this is difficult to reconstruct. This is difficult to manufacture, and with this kind of a constraint, with the rib reinforcement constraint, the idea is to generate a rib pattern. So the thicknesses are divided in a rib pattern over the entire structure, and it is possible to control the distance between the ribs and through a certain parameter. This is still in development. We plan it for this version. Finally, we have the optimization based on inertia relief method. The idea here is that the user can simulate and optimize unconstrained structures. So to do this in a static analysis, how do you create static equilibrium? This method uses the inertia of the structure itself. And this means you can analyze and optimize, for example, here, a free-floating aircraft. And we will support this from 2022. And it is possible to do this for 3D structures. Then I have some general updates here. The ANSYS interface and the Nastran interface of Tosca structure will be available only as controlled availability modules. This means if you want to use this, please get in touch with Dassault Systems, and it will be possible to use them, but you need a special authorization from this version onwards. Tosca Fluid is also made as a controlled availability module, which means, again, that authorization is required. And finally, we are now able to read the results, the optimization results from our internal binary database, which means we are one step closer to removing dependency from ASCII files. This is just an ongoing a project to improve our performance, our runtime performance. With that, I'm open for questions.